Let's talk about the squeeze theorem. The squeeze theorem is a theorem that we can use to calculate limits. And there's a couple of conditions. The first condition is that we are going to need the function that we care about, which is going to be g of x, to be bounded from below by some function f of x and bounded from above by some function h of x near some point A. So if you look at our picture on the right over here, this green curve represents the g of x function that we care about. H of x is sort of an upper bound. That's the upper bound over here. And f of x is the lower bound over here. So you can see that when we're near the point A, g is sort of trapped or squeezed between f and h. Okay. The second condition that we have is that the limit as x approaches a of f of x is equal to some number L, and that is also equal to the limit as x approaches a of h of x. So this is basically saying that the lower function f of x is going to some number, and the upper limit h of x is also going to that very same number. So if I were to label my picture over here on the diagram, I'm basically saying, oh, that point right there, that y value is L. Now, the two parts that we've just stated, these are the conditions of the theorem. Okay, and if these conditions are satisfied, then we have a conclusion. So this is how if-then statements work. The if part is the conditions, and the then part is the conclusion. And what is the conclusion? The conclusion is that the limit as x goes to a of g of x, the function we actually care about, the function that's squeezed in the middle, this guy is also equal to L. Okay. So the idea is if the top function and the bottom function both go to the same number, then g of x is squeezed in between those two functions, and g of x must also go to that number. Why don't we take a look at example 10? Example 10 is not the simplest example, but it is a good example. And we could apply the squeeze theorem to solve this problem. So what we're going to do is we're going to develop it step by step. When I look at this example 10, I see I need to calculate the limit of x times cosine of x. Now I'm going to start working with cosine of x and build up the function there. So I know that cosine of x is going to be bounded between -1 and 1, right? You know, remember that when you look at the graph of cosine looks something like this. You know, it's like a wave that keeps repeating itself, and the upper number is 1, and the smallest it gets is -1, like that. All right. So what I want to do is I want to multiply by x across the inequality. Now we have a slight issue here. When you multiply by a negative number, it's going to reverse the direction of the inequality. And when you multiply by the positive number, it's going to maintain the inequality. So what I'm really going to do is I'm going to split this up into two pieces. I'm going to calculate the limit as x approaches 0 from the positive side of x, cosine of x first. So when x is a positive number, what I can do is I can take this inequality, I multiply across by x, and I'm going to get this. I'm going to get negative x. This is less than or equal to x times cosine of x, and this is going to be less than or equal to x over here. So we're really saying, if you look at our theorem above, that x is going to be the h of x, and negative x is going to be our f of x. And when I take the limit as x approaches 0 from the positive side of x, well, that's just going to go to 0, right? So this guy goes to 0. And what happens when I take a look at negative x? If I have negative x is still a polynomial. So we learned that you could just, for polynomials, you could just plug in the number. So when I plug in a 0, negative x could be negative 0. Negative 0 is the same as 0. So this also goes to 0. So this means that my g of x function, which is what I'm trying to calculate the limit of, this middle part is g of x, this guy is squeezed in between these, and this also must go to 0. So I can conclude that the limit as x goes to 0 from the positive side of x cosine of x is equal to 0. This is by the Squeeze theorem. That's just one of the two one-sided limits. So now I want to take a look at what happens if I come from the left. So when I come from the left, I'm going to have the limit as x approaches 0 from the negative side of x cosine of x. And this time, I'm going to multiply my inequality. Let me rewrite it. Negative 1 is less than or equal to cosine of x, which is less than or equal to 1. Remember, cosine is bounded between negative 1 and 1. But when I multiply by a negative number, that's going to reverse the inequalities. So what we're going to have is we're going to have negative x is greater than or equal to x cosine of x. And that's greater than or equal to x. Now this is true. This is a, I'll put a little comment here. Since x is less than 0, we reverse the direction of the inequality. All right. So things have changed a little bit this time. This time, my h of x is actually the negative x, because that's the bigger guy. This is h of x. My f of x is actually x. You got to remember, we have negative values here, so that's why it works that way. And then both of those guys still go to 0. So that means that the thing inside the middle must also go to 0 by the Squeeze theorem. Okay, so now I could say the limit as x approaches 0 from the negative side of x cosine of x is also equal to 0. And this is, again, by the Squeeze theorem. So since the limit from the right is equal to the limit from the left, we could say that this means the limit as x goes to 0 of x cosine of x is equal to 0. So I hope this Squeeze theorem example makes sense to you. In general, we had to break it up into two cases because this x is both positive and negative around 0. So if this was an x squared, I wouldn't have to do two separate things because x squared is always positive. So I could just multiply across by x squared without worrying about the direction of the inequalities. All right, folks, we will look at this more in class, and you'll try an example yourself, and I'll be able to help you through that example if you get confused. Take care, everyone.